Now let us resume again your engineering mechanics lessons, solving numerical problems from engineering mechanics. Problem set 2.6, solution to 2.95. Some of you have suggested to move on to problems on friction. I will move on soon, and center of mass from next week. Now 2.995, a vertical prismatic bar. This is the original figure given in the book. This is the prismatic bar AB. All throughout the cross section is same, so it is called prismatic. And is negligible weight. Its weight is not to be considered. And its length is L. The prismatic bar AB has a length L, from A to B is L, is hinged to a cylinder of radius R. This is a cylinder, radius from here to here is R. This is the initial position. Hinged at A, radius R at A, and supported at D. This prismatic bar is supported at D by an elastic spring. This is the initial position of the prismatic bar. When this prismatic bar is applied with a force P here, as shown in here, then the length of the spring, which was from C to E, in the unstretched position, the length of the string has increased from E to D. From here to here, let this point is E. So there will be restoring force developed in the string, let it be F. By an elastic spring CD, in figure O, the stiffness of the spring is K, that is the spring constant, and the spring is undeformed when alpha is 0. If you look at this diagram and compare with this, when this angle alpha is 0, the prismatic bar is vertical, means the spring has not been stretched, so there is no restoring force here. When alpha is 0, the horizontal force P is applied to the bar AB. At this end B, a horizontal force P is applied. Once it is applied, the situation becomes like this. Now find the position equilibrium as defined by the angle alpha in terms of the applied force P, the spring constant K, length of the prismatic bar, and the radius of the cylinder. So I have explained you here. This is the initial position of the prismatic bar AB, that is vertical. In these positions, the spring is not stretched because the force P is not applied here, and alpha is 0. Now this is the final position of the prismatic bar AB when applied with a force P at the end B. So the spring is stretched. You can well imagine, if you compare this diagram with this diagram, this is the unstretched position of the spring. This is the stretched position of the spring. So the spring has been stretched from E to D in the form of an arc of a circle. So the stretched from E to D, so the arc ED will be R alpha. As we know, in a circle, if this angle is alpha, this point is B, this is O, then the arc AB, then this is theta, then theta will be equal to AB by OA, and that is what you studied in your school days, that is equal to AB by R. So theta is equal to, AB is equal to R theta. The length of the arc is radius times the angle, if angle is very small. Now P is the horizontal force applied at the end B. Now, so the spring will develop a restoring force, trying to regain its length, opposite to the direction of the stretch. So, as you have studied in your school days, the spring force F is given as minus kx, where k is the spring constant or the stiffness of the spring, and the negative sign only indicates F and x are opposite to each other. So here in this case, our x is equal to, the stretch is equal to from E to D, and that will be equal to R alpha. That will be equal to R alpha. So for x I put R alpha. The negative sign only indicates direction. Now resolve P, the applied force P at B into P cos alpha and P sin alpha. So let me show you here. At this point, if you draw a vertical line like this and another line like this, since this angle is alpha, this will be also alpha. So that is what I have shown here. Now P is horizontal and this dotted line is vertical. So this dotted line and this P, they make angle 90 with each other. And P sin alpha and P cos alpha, this line and this line, they are perpendicular to each other. This line and this line, they are perpendicular to each other. So this is the common angle. If I take out, then I am left with this angle is equal to this angle. Since this is alpha, therefore this will be alpha. So this is your P cos alpha, this is your P sin alpha. Now we'll take the moment of P sin alpha, P cos alpha about the point A. So since P sin alpha is passing through the point A, so P sin alpha will not have a turning effect about point A. So take the moment of forces about A. Contribution of P sin alpha to moment about A is 0 because this does not have a perpendicular distance from point A. It is passing through the same point. Now, if you look at the restoring force which acts all along the length of the spring has a perpendicular distance from A equal to the radius of the cylinder. Right. And your P cos alpha and P cos alpha and your P cos alpha from point A has a perpendicular distance that is from A to B, that is same thing as the length of the prismatic bar. So P cos alpha times L is equal to F times R for the restoring force. So K R alpha times R is equal to P cos alpha into L. So just R becomes R square, K R square alpha. Take P and L to the left hand side, so the cos alpha becomes K R square alpha over PL. So for this value of alpha, it is in equilibrium. Means it doesn't have any turning effect, means sigma tau is equal to 0. There is no linear motion, so no need to apply sigma f is equal to 0. So that is all about. So very soon I will move on to problems on friction and center of mass. All the best. Thank you.